Okay, as also for other cases, it is always a good thing if we can reduce the computational burden in order to be able, at least approximately, to do a simulation in 2D. And therefore, we have here some special cases in computational mechanics where we can reduce the full 3D problem to a 2D problem. And that I can show you now here as follows. So when we have here this part, I'm just looking here, we have the so-called plane stress case. And for the plane stress case, it is the following, as you can see here on this side, that we have a structure like this kind of cantilever, and we can assume that we have no dependency. So there is no dependency on the z coordinate, which means our mechanical strain in the normal strain is zz, as well as the two shear strains szx and szy is equal to 0. And according to our general relation between stress and strain, we then can reduce this constitutive law as shown here, in this sense that we have now just our two normal stresses and one shear stress, and get this reduced form of the constitutive equation. A very important part here is also that the load case and the boundary conditions are appropriate so that we are allowed to do it. And if you look here at the load case, we have a load case which is not changing in z direction. As you can see here, this is our z direction. And therefore, we can make such a cut and do a computation as shown here in the xy plane, which would just mean that it is like shown here, such a cut. And then we come up to this 2D model, which we can then, on which we can then perform the computation. Okay, so this is the so-called plane strain case if we have such a setup. So we reduce the three-dimensional case to a two-dimensional case. Not only computational time will reduce, but also the post-processing will be easier and so on. However, we can also have a 2D plane case, which we call the plane stress case, yeah? Instead of a plane strain case. And in the plane stress case, as you can see here, we have the relation that the stresses do not depend on the z coordinate. Yeah? As we are, for example, looking here, the z coordinate now is in the thickness direction of your structure, which means the two shear stresses and the normal stress sigma zz are equal to 0. However, we have to be careful in this case that the strain relation holds for the two shear strains, but due to our relation, the general relation between the stresses and the strain in the 3D case, we have a normal strain in z direction, which can be explicitly computed when we know the normal strains in x direction and in y direction as shown here. Again, what is important is clearly that the load cases are correct, which means it is appropriate in such a case that we can do then all the computation in the so-called XY plane according to our setup. Okay, so that gives us now the following. As you can see here, we again have here a relation where we just have here our normal stress in X direction, Y direction, and the shear stress as being expressed by our strains. And you see that now the entries are somehow different within our elasticity tensor here, this 3x3 matrix, and that is according to this relation here, because we have a normal strain in Z direction being expressed by the normal strain in X and in Y direction. On the other hand, again, as we can see here, we just have here 3 stresses and 3 strains to be computed. And the third case clearly is an axisymmetric case, also as shown here. Let's say you have such a setup where we have a cylinder, and the cylinder is, for example, fully fixed here at the bottom, and we have here the excitation on this structure as shown on this picture here with the external forces F, and then we can transform such a setup in this RZ rotational plane, and here you then can see it is a two-dimensional setup on which we have to do the computation. Due to the cylindrical setup, we will clearly go to cylindrical coordinates, where in general we have a R component, a Z component, and a circumferential component for the mechanical displacement. And according to the axisymmetric stress case, we can set that we have no mechanical displacement in circumferential direction. If you would have it, it would be a kind, for example, a drilling, and that clearly cannot be modeled as an axisymmetric case. So we have no displacement in the circumferential direction, and we have no shear strains where the circumferential direction given by the angle theta depends on. So these are also zero. Yeah, again, the load cases have to be accordingly, which we have seen on this side. For such a setup, this is fulfilled, so that we can transform it as we have seen here and just compute on the cross section. And the stress-strain relation we have here, we have to be a little bit careful in this sense, because we also have a strain in the circumferential direction and stress in the circumferential direction. Therefore, you have to use this constitutive relation between stress and strain. You note that the strains are computed out by the derivative of the mechanical displacements, and if the quantity itself is zero, that does not mean that the derivative with respect to this coordinate is equal to zero. So we have to be careful that this also has to be taken into account in the axisymmetric case. So now, taking this all together gives us the following formulation here. And the strong form is now, as we know, we have our partial differential equation, where we have here the two terms. We have the first term here, which are the inertia forces. So the second time derivative of the displacement is just the acceleration scaled by the density of the structure you are computing. And we have here our special P operator operating on the mechanical stresses, and we know that this has to be equal to some external forces, and this G here models any external volume forces. Any surface forces we will get in by the boundary condition. In addition, we have our constitutive equation. The constitutive equation giving us the relation between stress and strain by our material tensor C, which we have seen that for the isotropic case, it is just computed out the entries by the mechanical modulus E and the Poisson ratio nu. And importantly, that we end up at the partial differential equation for the mechanical displacement U. We have the relation between the strain and strain components and the mechanical displacement U by the same differential operator B here. Furthermore, we have boundary conditions in this sense that we can prescribe, for example, that the mechanical displacement has some value on the boundary, and we have to know it over the whole computational time we are computing, so it is still time dependent. A natural theoretical boundary condition would be that the mechanical displacement is equal to 0. All components, for example, which would mean we fully fix this part of the structure and it cannot move. And we can also prescribe some stresses on the surface of the computational domain, which we will discuss in detail shortly. And that can be done again when we use our Voigt notation, where we collect our 6 unknown stresses or 6 unknown strains in the algebraic vector, where we first have the normal components and then the shear components by such an operator n. And if you look at this operator n, you see it has the same structure as this operator b, but the entries are not partial derivatives with respect to x, y, and z. The entries are the components of the normal vector n, the x, y, and z component, but on the same positions as we have the derivatives in the b operator. Yeah, and since it is a time-dependent partial differential equation, we also need our initial condition as shown here. Since it is second order in time, it means we have to know the mechanical displacement u at time t equals 0 and the velocities as shown here at t equal 0. For most cases, we start here for u0 and u0 dot to be equal to 0 and start at the body being in rest. Okay, so in order to come up to the weak formulation, we again multiply, but be careful, multiply here means taking the dot product, the inner product. So the difference to the other partial differential equations we have discussed is that this partial differential equation is a vector partial differential equation. Up to now we just had scalar partial differential equations, and therefore the test function itself, u prime, is also a vector. And so you see we do an inner product of this test function with the partial differential equation and then integrate over the whole computational domain in order to get here this equation. Now, we just have to be a little bit careful. How can this be the case? We have 3 unknowns, the x, the y, and the z component of the mechanical displacement. With the dot product, we just get out one equation. So that is working in this sense that once you take a u prime as shown here, being, for example, just this u prime as a vector, just having here a u prime x component and 0, 0. And so you would get out here then a first equation. And then in the next case, you would take here, for example, a second. So let's call this u prime 2. And that would be that we just have here a uy prime component, and the z and the x component is equal to 0. So I call this test function u1. Then you have the test function u2. And at the end, we take also a test function. Okay, why is this away now? Very interesting thing, u3 prime, which would be 0, 0, u z prime. Okay, so let's try again. We can also get our u, not this one, sorry. Very interesting. Now, we get rid of it. And here I would have u1 prime. And now hopefully I get another color. That would be the test function u2 prime, the vector test function where we just have a y component. Okay, so and by this part, then it is possible that we get out 3 equations, and you see that this inner product then really makes sense. Still, as we know, it makes, we have here this term where actually when we substitute our mechanical stresses by the constitutive law, by the mechanical strains, and then the mechanical strains by the mechanical displacement, we have a second order spatial derivative. So it makes sense to do an integration by parts. And that means that now we have the p operator operating on our test function. Okay. In addition, we get this integral over the surface due to this integration by parts. And we clearly also have to incorporate here any displacement boundary conditions, which are so-called Dirichlet boundary conditions, where we prescribe the mechanical displacement on a part of the boundary called gamma E. And we have here also a second boundary condition, which we call the traction, and that is as follows, that the stress on the surface is prescribed, and we can prescribe there the stress on the surface, that has just a normal component or just tangential components. In this sense, we can prescribe normal excitations as well as shear excitations. Okay, so the natural boundary condition would be clearly a 0 interface stress, so that this part is 0, which means at this part of the surface, the body can freely vibrate and there are no constraints on it, no fixing of this part, and then this part of the surface integral will just vanish. On the other hand, this sigma n, the traction boundary condition with sigma n, has 3 components, very important. So we can have 1 normal component and 2 shear components. And a pressure load, for example, would be that sigma n has just a normal component. As you know, the pressure acts as a normal force on the body. And importantly, you have to put a minus because the pressure is always having a direction into the body. So it is a force direction into the body and not out of the body. Therefore, we have to put this minus. Okay, that means now that we have the following weak formulation. We assume that we have given initial displacement and velocity fields, and we are searching for the mechanical displacement field fulfilling this equation here, where we have our standard inertia term, the second time derivative of the mechanical displacement scaled by the density of our body, and we have here our classical term which we have obtained due to the integration by parts, where we have here our material tensor C and the P operator operating on the unknown displacement u and on the test function. And on the right hand side we can have any standard source term due to some force density, so some force density given, and we can have here our additional term on the natural boundary gamma n, which we have discussed here in this sense. So in this sense we can put traction boundary condition, which can have, for example, just a normal component, but can also have shear tractions, so which means that the forces per per square meter are acting within the tangential plane, so on the surface. Okay, so the next steps are, as we have discussed, in also for the other partial differential equation, the only thing now is the following. We write here our basis functions in bold, which just means the following. We have clearly, for example, for 2D, we have to approximate the x component of the displacement and the y component. And then actually this n is written as a diagonal matrix. And in a standard approach, you use the same basis function for approximating the x component of the displacement as well as the y component of the displacement. But that would be an additional freedom for some special finite element procedures. You could use different basis functions for the different components of the mechanical displacement u. But in the standard approach, you clearly use the same basis function of the same order as just written here. Okay, for the 2D case. And for the 3D case, then we have just a 3x3 matrix and using the same basis function also for the z component of the mechanical displacement. So if we now substitute this ansatz into our weak formulation, we come up at the end at a system of ordinary differential equation of second order. So x here is just a vector collecting all the unknowns of all the displacements at the finite element nodes and the displacements concerning x, y, and z component. And we have here a so-called mass matrix that we get out due to the inertia forces. So the material parameter entering the mass matrix is exactly the density. We have the stiffness matrix K, and in addition, what we have edited here, and we had not before, is here the so-called damping matrix, which we now just have edited here, and which is multiplied by the time derivative of the mechanical displacement, so by the velocities. And the standard approach here is to use a so-called Rayleigh damping model. And the Rayleigh damping model, this damping matrix D is computed out by scaling the mass matrix M by some value, scalar value alpha r, and the stiffness matrix K by some scalar value beta r, r standing for Rayleigh damping. That is a standard approach which does not really increase the computational burden of your problem you want to solve, and fits well in a lot of problems in practice. So it is just a question then how to get these two parameters alpha r and beta r, but there are some special possibilities with experimental setups so to get these parameters there via the loss factor of the material. Okay, so now collecting this all together, we have this as our semi-discrete Galerkin formulation, as it is also called, because we are still continuous in time. We have here the second time derivative with the two dots written here. So these are the accelerations, the unknowns, the unknown velocities, and the unknown mechanical displacement. And now just starting from this equation, we can have and perform a static analysis, which means that all time-dependent quantities are set to 0. So we just have to solve here this equation that the stiffness matrix multiplied by the unknown displacements is equal to the right-hand side, which collects all the forces, volume forces, and surface forces. And that would be a static analysis. On the other hand, a standard analysis clearly would be that we want to get the dynamic behavior of our sensor, actuator, whatever system we are investigating in. And then we have to do a transient analysis, which means that at the end we will get up such an algebraic system of equation of some so-called effective mass matrix. We will discuss how we will do the time discretization, but it will be very similar as we have discussed for the heat equation. The difference clearly is we have here a second time derivative, and for the heat equation we just have a first order time derivative. And with such a transient analysis, we then have also to discretize this semi-discrete Galerkin formulation in time and compute then for each time step of interest our solution. Sometimes the excitations are harmonic excitations, and then it makes sense to go over to a so-called harmonic analysis. So that means we have our excitation, which can be written by some value f, which has absolute amplitude value and phase, and it is changing by this exponential function. And when we use such an ansatz as written here, and we put this ansatz into our semi-discrete Galerkin formulation, then we know that this exponential function e with exponent j omega t cancels out, and we come up to this algebraic system of equation where x is now a complex unknown displacement, and we have, as we can see here, directly the stiffness matrix, the damping matrix scaled by j omega, and the mass matrix scaled by j omega to the square, which means minus omega squared. Here it is clear when you do a harmonic analysis, we get the steady state for a harmonic excitation, so we cannot model or compute here any dynamic effects which are really transients. For example, when you switch on a motor at the beginning, but after some time it will work at the steady state, and then this is a very appropriate analysis. Yeah, and importantly is also, especially for mechanical systems, to be also able to do an eigenvalue analysis with the eigenvalue analysis, we are then able to get the resonance frequencies of your system and also the mode shapes, so how the vibration of your structure looks like at these different eigen frequencies, which are the eigenvalues of your eigenvalue problem. And as you can see here, mostly what you do is, and you compute the free undamped oscillations, because when you also take into account the damping term, you come up to an eigenvalue problem, which is a quadratic eigenvalue problem and which is not as easy to be solved. So that's why mainly for eigenvalue analysis, you perform it for the undamped case, setting the damping matrix D to 0. Okay, so static analysis, as already told, means we have an excitation which does not depend on time. We have just to solve here for the system matrix being the stiffness matrix K here to get all the mechanical displacements within our finite element node. So there is no time dependency, and we solve one linear system as shown here because we have not modeled any nonlinearities. So for some cases, this is even appropriate when we have a slow forcing, meaning that the dependency of the force vector F on time is in such a case that the forces are almost not changing over time. So then we also can approximate it, and instead of a dynamic transient analysis, we do just a static analysis. Okay, the second case is this harmonic analysis. That's an analysis we extremely like to do also for electromagnetic systems, and that is also very often done for mechanical systems, especially in such a case that we can express our forcing as a time harmonic forcing as written here. We have to be careful then clearly that this value we get out more or less is complex. Yeah, and also as we are speaking, we get out amplitude and phase of the mechanical displacement for all three components, X, Y, and Z component in all the finite element nodes. Okay, so that is an approximation in this sense that we do not take into account any transients, and we have here the steady case what we can compute out, and that clearly we can compute for each forcing frequency omega, and so we can compute it for a lot of different frequencies and can get then the so-called transfer function, which is the displacement over the excitation force. Yeah, and we have to solve a complex valued linear system of equation for each frequency of interest. And the results are then as follows, that we have more or less the oscillation amplitude and the phase phi now is also written in bold because we clearly will have different phase angles for the mechanical displacement at the different locations. We can also write it down and back into the time domain, and for that we know we have to take the real part of this complex displacement amplitude x hat and have to scale this with with the exponential function with exponent j omega t, which means what we get out are the amplitudes cosine omega t and this phi vector being the phase at all the different finite element nodes for the three components x, y, and z of the mechanical displacement. Okay, and the eigenvalue analysis is that we set the right-hand side equal to 0, and we just solve here this system of equations as we have obtained before. You see, it is exactly what is written here. We just have cancelled out here the damping in order to make it to a simpler eigenvalue problem, and then the solution out of it will give us the eigenfrequencies and the eigenvectors to it, the shape of the vibrations of your body. Okay, so we will have only certain solutions are possible clearly under these assumptions, which will be the eigenmodes what we get out, and we solve this eigenvalue problem with the eigenvalue lambda in this sense with the stiffness matrix K and the mass matrix M, and get out the natural or resonance frequency, as we call it, and we get out the eigenvectors, which are the so-called oscillation modes. You will see when you do the exercises and do practical computations for any structure. Okay, so these are in general the 4 analysis methods we have. Also for other physical fields you can apply it. For the mechanical fields, it is a standard that you really apply all 4 analysis: a static, a transient, a harmonic analysis in the case you have harmonic excitations and you are just interested in the steady state, and the eigenvalue analysis is a classical analysis for mechanical structures, because you are interested at which frequencies you have resonances and how then the oscillation modes look like. Okay, what remains is now to look back at the transient analysis, because for the transient analysis we now have to discuss how we do and approximate the continuous second time derivative, and at which time we evaluate the displacement vector x and the right hand side f. We assume here that both our mass matrix are constant, doesn't depend on the mechanical displacement, velocity or acceleration, and the same holds true for the stiffness matrix. So the approach is the same as we already have discussed for the heat equation. We subdivide the time interval in small intervals, and the standard approach is to have a constant time step size delta t, and so the whole computational time t is then divided by your m time steps to get delta t. How we do the approximation of a time derivative? You could do it the same as we have done for the space. That would give you the so-called space-time methods, discretization methods. However, we, for the standard approach, the time discretization is just done with finite differences, which means, as you see here, the following, that we approximate now our second continuous time derivative. In this case, that we evaluate it, our mechanical displacement at the time tn plus 1, at the time tn, and the time tn minus 1, and normalize it by the time step size delta t squared. And this is mainly written in this sense, as shown here in short form, that you have an index, and we know that we have this relation that the index m plus 1 means we have to evaluate here our mechanical displacement at the times the tn plus 1. Okay, so very similar as we have done also for the heat equation, we now also have to decide at which time point we evaluate our displacement and the right hand side, and to get the highest accuracy, it makes sense to do a so-called convex linear combination between the time step Tn and the new time step Tn plus 1. So exactly the same as we have done also for the heat equation. So we have now a so-called time integration parameter alpha h. So you see we once have our system that we have the stiffness matrix and multiplied with the vector of our mechanical displacements evaluated at time step m plus 1, scale it with alpha h. Then we evaluate it at time step Tn and scale it with 1 minus 2 times this alpha h. And last, we evaluate it at the time step Tn minus 1 and scale it with alpha h. And just the same procedure we also apply on the continuous right-hand side f of t to get the discrete in time right-hand side. So you see we have also here the same convex linear combination between Tn plus 1 and Tn minus 1. And now when we collect all our terms with the new mechanical displacements we want to compute at time step n plus 1 and let it on the left hand side, and all the others we put to the right hand side because we assume that we already know the mechanical displacements at time step Tn as well as time step Tn minus 1, then we get here this system as shown here with one big mistake. I just see here it should be the stiffness matrix clearly, otherwise it makes no sense. So we see our new system matrix is the mass matrix M, and we have in addition our stiffness matrix here scaled with alpha h, our time integration parameter we will discuss shortly, and delta t, our time step size squared, and all the other terms we have put on the right hand side because clearly we assume that we know our force vector at all the time steps of our computation, and the other terms which are in this line and this line we clearly also assume to know because we know already that the mechanical displacements at all the nodes for time step Tn as well as the time step Tn minus 1. Okay, so a possibility would be to set this parameter to 0, because when you set this parameter to 0, just when we go back, then you clearly see that this will cancel out, this term will cancel out, and the whole system matrix will be just the mass matrix. And in this sense, we would have to solve this algebraic system of equation as written here, because we have set alpha h to 0, and there is a tilde on it. So this will be an explicit time discretization approach. However, since M is not a diagonal matrix, but it is a sparse matrix, we have not gained much, but what you can do here is to transform the mass matrix M to M tilde. M tilde is a pure diagonal matrix, and you can compute the entries of this M tilde as follows. So this M tilde, let's call it I j. The entries, sorry, I didn't want to have the J and okay. So I'm now not allowed. Okay. Okay, my new PDF viewer has some problems with it. Anyway, I try to rewrite it. So this M tilde I is nothing else as the sum over J Mij, which means you just sum up for each row all the entries and put this on the diagonal, and you set all others other values to 0, which means this then becomes a diagonal matrix. Okay. Because if this M tilde is a diagonal matrix, then you don't need the algebraic solver. You simply scale the right-hand side by the diagonal entries of this matrix, and then such an explicit scheme makes a sense. However, you have some stability criterion to be fulfilled, and that's the classical CFL condition according to Courant, Friedrich, and Levy, and that is given by this sense that delta t should be smaller than 2 over the square root of the maximum eigenvalue of M inverse scaled by the stiffness matrix. This clearly would be too much that you really compute it. However, what we can find from analysis is that it scales by the order of the grid size to the power of -2, which means the smaller your grid elements are, the larger the eigenvalues, and the smaller delta t has to be. The engineering approach, you can show that this restriction can be simply computed when you know the wave speed, and for this you mainly use the longitudinal wave speed. As you know, in the solid body we have quite a lot of different waves which can propagate longitudinal wave, transversal waves, you can have surface waves, and so on. And then it is easy as follows. You just have to fulfill here this criteria. Delta t should be smaller than your grid size over the longitudinal wave speed, which means within one time step, the wave should not move over one finite element. That is this very simple relation. In computational mechanics, you mainly apply such a time discretization, explicit time discretization for crash simulations. For almost all others, we will do an implicit method, and the implicit method of choice is the so-called Newmark scheme, which means you first compute the predictors. Therefore, you have this tilde for the displacement and for the velocity. And you see you compute it out of already the values you have obtained in the previous time step. So you need just to store the previous displacement and the velocities and accelerations. And then you solve your system now with a system matrix we call K star. It is the so-called effective stiffness matrix, which computes out of the stiffness matrix itself, the damping matrix, and the mass matrix. And these gamma h and beta h are integration parameters for this time discretization scheme, and as a standard you use beta h equal 1/2 and gamma h equal 1/4, and that gives you then second order accuracy. Okay, and after you have computed the new displacements, which are our xn plus 1 vector, you can also compute out the new accelerations as well as the new velocities. So x point n plus 1 and x double point n plus 1, as you can see, by also using the new solution xn plus 1 and the predictors x tilde and x dot tilde. So this is the standard scheme, so-called NUMAC scheme, which we also have implemented within our software. Okay, so you see that also the time discretization of for the mechanical partial differential equation is not as complicated, and in order to get here the highest accuracy, as I have told you, again I write it here, you use beta h equal 1/2 and gamma h equal 1/4. Okay, so this was an overview about the mechanical field. We have seen all the different constitutive relations we have between mechanical stress and strain, and that for some cases we can reduce the full three-dimensional problem to a two-dimensional problem, in this sense that we have a plane strain or plane stress or an axisymmetric setup, and then result in a two-dimensional computation. Anyway, the mechanical displacement is a vector. It has three components, the x, y, and z component, and therefore also our test function is a vectorial test function, and we have seen how you can get out by the dot product also three equations, because we have three unknowns, x, y, and z in the continuous setting, and the discretization is similar as we have discussed for the scalar partial differential equation. We just have to approximate each component of the unknown displacement vector, the x, y, and z component, and in the standard approach you use there also the same basis function for the three different components ux, uy, and uz. Time discretization is similar as we have discussed for the heat equation. We have just a second order system of ordinary differential equations, and here the optimal scheme to be used is this NUMAC scheme, which gives you at the end then an algebraic system of equation you have to solve for each time step of interest. Okay, so what we can finally do today is then also discuss the coupling between the mechanical field and the thermal field. We already had there some preliminary relations concerning the constitutive law via the expansion coefficient. And that we want to discuss here. And as you will see, we will just take into account the forward coupling from the thermal field to the mechanical field, which is in most cases appropriate, especially for problems we are interested in, for example, the heating up of semiconductors, especially in power electronics. And there, as I have told you, the main problem at the end are the mechanical stresses coming up due to the temperature distribution within the IC. Okay, so just summarizing the heat equation, we know that our heat equation looks like this, and our source term is shown here on the right hand side was coming up from our electric flow equation. So when the electric current is flowing through your device, then clearly we have Joule's losses, and for this we have to solve a simple Poisson equation and then get the heat losses, which are the right hand side. And in a coupled computation, we have to take into account in the computation of the electric potential that the electroconductivity also depends on temperature. Okay, so let's see in our case that we know already our volumetric heat sources, which are the Joule's losses, and we have discussed how to solve this heat equation. Okay, now concerning the thermal strain, we have the following, that these thermal strains are computed out of our thermal expansion coefficients, which are just collected here in a matrix, or so-called tensor here. And for the simplest case, this alpha is the same for all the three coordinates, so for the x, y, and z direction. And it can also be very general, as written here, that we have different entries for the different directions. However, for most cases, we can set these coefficients to 0, and even if the thermal expansion is different in the different direction, it just gets here a diagonal matrix which scales the temperature difference to a reference temperature by this thermal expansion coefficients and getting then the thermal strains. Okay, and even for most cases, it is isotropic, so the alphas here are really the same for all three directions. Okay, the elastic strain is then, as written here, the total strain minus the thermal strain, and then we put this into our Hooke's law. So in the standard relation between the mechanical stress S and the mechanical strain, mechanical stress sigma and mechanical strain S, and the relation, as you see here, is on the elastic strains. And the elastic strains can be expressed by the total strains, as we know, and the difference with the thermal strains. Okay, so when we now use the constitutive relation, as written here, with our, according to Hooke's law, with our material tensor C, as we have used in mechanical, in the mechanical system, then you see that we get out here now the relation between sigma and the total strains and the temperature differences, which is, as we know, the temperature minus a reference temperature. Yeah, for a very general case, these expansion coefficients we also collect into a vector with the 6 components. This is according to the Voigt notation we have. However, as I have told you, in a lot of cases, we have here all our values according to shearing equal to 0. And for a lot of cases, even we have an isotropic material, so alpha 1, 1, alpha 2, 2, and alpha 3, 3 is just the same. There is also a reaction from the mechanical field to the thermal field, and this is according to a dissipation power density, which is driven by the stress rate, so the change of the mechanical stress with respect to time. But for most cases, this is not necessary to be taken into account, which means, especially in our application, that we first can compute the temperature field, and then in the next step, we can compute the mechanical deformation of our body of investigation according to this temperature field with the thermal strains coming up to a temperature distribution within our body. Okay, so the temperature distribution clearly causes the thermal strain. According to the thermal strain, we will then have thermal stresses and the deformation of our body. If, for example, our mechanical body in this sense has more or less no influence on the temperature distribution. For some cases, we have seen that we perhaps have to take into account the coupling term coming from the mechanical field, which is driven by the stress rate, so the change of the mechanical stresses with respect to time, which is, however, in most cases very small, which means that we can model our coupled field problem by a one-way coupling as written here. So you first compute your temperature field within your semiconductor, for example, and then compute the mechanical displacement. Now, according to our mechanical weak formulation, that means that we have this additional term to be taken into account, which is coming from a temperature difference between the temperatures within the body and the ambient temperature, and that gives a rise to our thermal strains multiplied by the mechanical material tensor. It will be the thermal stresses, and it is, as you can see here, then scaled with the same B operator and the test function, which means at the end it is just an additional right-hand side term, additional volume load, which results here to this additional right-hand side term in our weak formulation, and then clearly going further into the discrete system will end up here in additional loads on the mechanical structure in the discrete setting. Okay, so the thermal stress clearly arising depends also on the boundary condition. It's clear if you perhaps have an unconstrained structure, which means there is no fixing of your mechanical structure, then it will be stress-free, so the temperature load will not result into mechanical stresses, but it's not reality. In reality, you clearly have at some parts of the boundary a fixing of your structure, and then clearly the stresses will come up. Important are the temperature gradients. So in some analysis and investigations, you first, as I've told you, you compute the temperature distribution in your structure according to some heating up, for example, by the Joule's losses. And the important post-processing result here is to look at the temperature gradients, because if you have strong temperature gradients, then clearly we will also have strong mechanical stresses. and it is clearly significant, especially for metals, if you reach the yield limit, which is about a temperature difference of 150 Kelvin. Care has to be taken for all the computations to specify appropriate boundary conditions, and appropriate boundary conditions means also you have to stay in one unit system. You can use, as written here, Kelvin, or you can use degrees Celsius, but you are not clearly allowed to switch between these two and have a mixing. So you should keep to one unit concerning the temperature, which can be Kelvin or degrees Celsius. I always advise to use Kelvin because it makes sense and gives you then not any further input mistakes that you perhaps mix it up and give some values in Kelvin and some in degree Celsius. As you know, the thermal stresses are driven by the temperature differences, and so it's important that you keep here to one system, specify the values in Kelvin or degree Celsius. I always advise to keep to Kelvin. That makes sense. Also, when you look up at different material tables, mostly the expansion coefficients are given as a with the unit in using Kelvin and not degrees Celsius. Okay, so we have now also seen that we can have the full chain for the investigation of especially power electronic devices, that you start with computing the electric flow equation to get the Joule's losses. With the help of the Joule's losses, you can compute the temperature distribution within your device, and then in a further step, with the help of the temperature distribution, you can solve the mechanical equation where this temperature distribution enters at the right hand side of your mechanical system as an additional load on the structure, and that will give you the deformed structure of your device. And especially important there is to compute in a post-processing the mechanical stresses and look how large they are and if they are below some value, in order that you still be within the elastic behavior and not go perhaps towards a plastic behavior, which at the end perhaps will break your electronic device. Okay. I should also mention that next week there will be no course, no lecture course, because I have a PhD defense, and it was not possible to put it at another date. So we will see again in 2 weeks, where we will then start with the description of piezoelectric materials, which are heavily used for sensors and actuator applications. And we'll discuss there how the electrostatic field couples with the mechanical field via an extended Hooke's law. So the mechanical stress will not only depend on the mechanical strain, but it will also depend on the electric field. And there it will then be possible to model and numerically simulate the dynamic behavior of piezoelectric actuators and sensors. Okay, for today we have finished now. If there are still some questions, so I don't see anything in the chat, I will try to resolve the problem that you don't see your points of the exercises you have submitted, especially task 1. I thought I have resolved it, but there seems to be still some sub-menus where I have to switch on so that you see it. I will try to resolve it. Okay, if there are no further questions, I will be still online as each time for some minutes. Then I wish you a nice evening. Thank you.
Thank you. Good evening.